Linear transformations sit at the heart of linear algebra. They're the reason matrices matter at all. They describe how entire spaces stretch, rotate, or collapse. Once you build an intuition for what linear really means, the rest of linear algebra suddenly becomes far easier to understand. Hey everyone, welcome back. If you're new here, I'm Oliver, a computer science student and tutor who used to struggle with exactly these concepts. Now, I make short explanation videos to help you build intuition faster than I did. Today we're tackling one of the most fundamental ideas in linear algebra, linear transformations. What they are, why they matter, and how they reshape entire spaces. Before jumping right into linear transformations, we need to understand what vector spaces are. A vector space is simply a place where vectors live and behave predictably. You can add vectors and scale them, and the result still lands in the vector space itself. So formally, the vector space is a set, and each element of that set you can add to another element of that set and scale them, and the result of it will still be present in that set. One example for a vector space would be the real coordinate space, or real coordinate n space, which has n dimensions. Now, in this case, I chose specifically the R2, which is a two-dimensional real coordinate space. It is composed of vectors that look like this, every one being composed of two individual numbers, which come from real numbers. So vector spaces are defined over other structures, one of them, for example, being the real numbers, but I will not get into the specifics here, as will be too detailed for a single video. These vectors, their addition and scalar multiplication, is defined in a way that adding two of these together, we land in this space again. Another example of a vector space is the set of all polynomials, in this case of degree 2 or lower. Degree 2 meaning that the largest exponent in our polynomial is 2. Here you can see what the polynomial would look like with variable coefficients. And these coefficients come from our real values. So again, this is a vector space defined over the real values. You can again take any one of these polynomials and add it to another polynomial or scale it, so multiply it with a real number, and you will again land in this vector space. So that's an important aspect of vector spaces, is that they're closed with regard to addition and scalar multiplication. Vector spaces can also be somewhat more abstract. I just wanted to mention this, but will not go into detail. There are certain axioms for vector spaces, so that for any set, you can check whether these apply, and in case they do, you have a vector space. To keep this video a bit shorter, I will not go over them today. Now that we know what a vector space is, we can get into linear mappings. So first of all, we will see that a mapping which we've defined, so T, we define it as having the domain V and the codomain W. So the inputs of our function come from V and the outputs land in W. Now both V and W are vector spaces in our case. So they behave in the way which we've described earlier. And now we assume that these vector spaces were defined over our real numbers. And what it means for this mapping which we've defined to be linear is that these two rules apply. The first condition here tells us that when adding two vectors u and v, and these can be any vectors from our domain, so v, that we can just pull out this addition. This equality holds for any two vectors. Adding in our domain and then applying this function is the same as independently applying this function and then adding in our codomain, so in W. That's where this addition here is happening. And then our second condition, the scalar multiplication in our domain is the same as the scalar multiplication in our codomain. So whether we scale our vector in V or we do this after having applied the function t in W, it is the same. And this is true for all V in our vector space and all A. And these are our scalars. And our scalars come from the set that our vector spaces are defined over. Together, both of these conditions can be combined into one equation, this one here. We have the scalar multiplication and the addition being defined in one rule. And if you are able to show that this equation holds for all vectors in our domain and all scalars, then you've shown that a mapping is linear. A consequence of our second rule is that in case our input is the vector 0, then the output has to be 0. We can show this by plugging in here 0, noticing that we can pull this apart into a multiplication between a scalar 0 and any vector v, so this will still equal to the vector 0. Setting in 0 for our alpha on the right side, we get a 0 here. And again, multiplying with any vector here, we get 0 on the right-hand side. So our linear transformation has to map the value 0 to 0. Matrices are a standard example of linear mappings, but any mapping between vector spaces, respecting the rule, is a linear mapping. I will briefly show you for when we have the given v and w here, so vector spaces R2, that matrix multiplication is a linear mapping. We will say that our mapping goes from v to w, and it's defined as t applied to v being the same as multiplying a times v, where now a is a matrix of size 2 times 2. If we now write this equation, so t alpha times u plus beta times v, and then we plug in our definition of t, we get a times alpha times u plus beta times v. And given our rules for matrices, we can actually divide up this multiplication or the addition. So we get a times alpha times u plus a times beta times v. Then we can pull our scalars to the front to get alpha times a times u plus beta times a times v. And then what we have standing here, a times u and a times v, is just the same as applying the function. So we receive alpha times t applied to u plus beta times t applied to v. So exactly this condition. And since we've not made any assumptions about alpha, beta, u, and v, this holds for all of them. Now, here I've sketched in a simple case for a linear transformation, where we go from a one-dimensional space to a one-dimensional space. In this case, our first dimension is the x, so our domain, and the second dimension is this y-axis, which is t of x, and would be our codomain. Now, this green line here would be a linear transformation. I will not get into the mathematical reasoning in this video, but two indicators that show that this is linear is that the 0 vector maps to 0, and also the relationship between t of x and x can be described by a line. Now, for this red line, x and t of x technically still have a linear relationship. However, now our 0 vector is no longer being mapped to 0, but to a non-zero value. So this, in fact, is not a linear transformation. Now, for this case, we do map 0 to 0. However, our transformation is no longer linear. X and t of x are not related through a line, but a parabola. Now, drawing two-dimensional transformations is not as easy anymore. However, I'll try to explain what is legal. A linear transformation can, for example, stretch our vector v. So in this case, it would be stretching this vector to something like this. Can also squash it, so shortening it to this size here. Rotate it by transforming this point to one somewhere here. And collapse dimensions entirely. So for example, mapping it to here, where our value of the second dimension is completely disregarded. And this can also be done with combinations. So for example, what I've sketched in here is both a rotation and a stretching. But bending, like x squared, as we've seen in the previous example, is no longer linear. So linear maps can stretch, squash, rotate, mirror, and collapse dimensions, but bending is no longer linear. So the moment straight lines bend, it's no longer linear. And that's exactly why it's called linear. Our relation has to, on some level, be linear. So straight lines stay straight, but their direction and length can change. To better see what linear mappings do to space, I will show a couple of examples. And I think in this case, it's best to look at what happens to the basis vectors to understand what happens to the entire space. For the case of scaling, when we take our basis vectors, so our first basis vector having zeros except for the first entry, and our second basis vector having zeros except for the second entry, we see that for the first basis vector, which would be defined by this point here, so a vector like this, we scale our vector with a factor of 1.2. This vector here transformed into the vector which is induced by this point. So this vector here, meaning we stretch into this direction by a factor of 1.2. And for our second basis vector, we see that it's scaled by 0.6, meaning that our second entry is shortened from 1 to 0.6. And now we know that our transformation defines in this direction a shortening and in this direction a scaling, meaning that if we take this point, for example, we know that it will shorten our vector in this direction and lengthen it in this. So our transformation transforms the vector induced by this point, so this one, to the vector induced by this point, this one. In our second example, we'll look at the rotation. When we look at the basis vectors, so 1, 0 and 0, 1, we see that our first basis vector is transformed to 0, 1, so moving from this point to this one, and our second basis vector, this one up here, is moved to -1, 0, so here. And this is exactly our rotation. Our transformation T does a 90-degree rotation counterclockwise. Another example would be the reflection. In this case, we would be reflecting across this diagonal. So our point 1, 0 gets transformed into 0, 1, and our point 0, 1 gets transformed into 1, 0. And we would see that for any point that's on this diagonal, which we are reflecting across, that nothing changes. Because we take a point on this side, move it across by reflecting, and then land here. But if our point is already here, reflection doesn't change anything. And I will show this briefly, also showing you again this first rule of our transformation. So we spoke of the point 1, 1, and now we know that we can divide this into an addition. So t of 1, 0 plus 0, 1. If we apply our rule for linear transformations, we see that t of 1, 0 plus t of 0, 1 is our result. And plugging in the values which we've got here, we get 0, 1 plus 1, 0. So again, 1, 1. The same point as we started with. So we see that just knowing what happens to the basis vectors, we can apply that for points by pulling them apart and writing them in terms of these basis vectors, which we can pull apart because of our first rule, and thereby define what a certain transformation does. So generalizing this for any vector with entries v1 and v2, we can apply the strategy we used before, pulling apart our basis vectors here, apply our rule here, and get our result v2, v1. So just based on what the transformation did for our basis vectors, we were able to define what it does in any case. So the image of our basis vectors determines all the behavior, since all points are just linear combinations of these, as we see here. So I've mentioned briefly that linear maps can collapse dimensions. And this collapsing of a dimension, for example, this here, it gets rid of an entire direction, since this one here, so any point on this line, will just get mapped to the same point, the origin. So some linear transformations quietly erase entire directions. And that's exactly what the kernel or null space describes. If you want to learn how this ties into the structure of a transformation, check out my video on that next. You'll also find a full linear algebra playlist on my channel if you'd like to explore the topic more deeply. If this was helpful, consider subscribing so you don't miss future videos. And as always, thanks for watching.